Hello students, myself Amrita Dhar, Assistant Professor of Electrical Engineering Department of Greater Kolkata College of Engineering and Management, JIS Group.
In this video, I will discuss about power and energy output for the driving axles. This topic is included in Module 1 of the subject Utilization of Electric Power and subject code is EE-702. Mechanism of train movement. Mechanism of train movement. Now first I draw a diagram. Now this area is 1, this area is 2, this area, I number this area as 3 and this area 4. Now what is 1? 1 is armature of traction motor. Area number 2 is pinion of motor. Number 3, gear wheel. And number 4 is the driving wheel. So this is the armature of the traction. This is the pinion of the motor, this is the gear wheel and this is the driving wheel. Okay, now this figure shows schematically the essential driving mechanism of an electric vehicle. The armature of the traction motor has a pinion meshed with gear wheel and driving wheel. This pinion is meshed with gear wheel on driving wheel. Now suppose the traction motor exerts a torque T which will be transmitted to driving wheel through the gear. The torque T is equals to F1 R1. F1 is the tractive effort and R1 is the radius of the pinion. Okay, radius of the pinion is R1. Now gamma is the gear ratio. Let gamma is the gear ratio. Now which is equals to speed of motor pinion in RPM by speed of the driving axle in RPM, which is equals to capital N1 by capital N2. Capital N1 is the speed of the motor pinion in RPM and N2 is the speed of the driving axle in RPM. Now if F is the tractive effort at the driving wheel and R is the radius, then F into R is equals to F1 tractive effort at the pinion, R is the radius of the pinion, and eta. Now what is eta? Eta is the efficiency of transmission. Efficiency of transmission of power from motor to driving axle. Now R is the radius of the gear wheel fixed to the axle. Now what is R? R is the radius of the gear wheel fixed to the axle. So therefore F is equals to F1 R eta by R. Suppose this is equation 1. From equation 1 we get this. Now this is now F1 R1 is equals to T. So I can write this equation as this equation. And what is F1 R1? F1 R1 is torque T R into eta by R into R1. Now gamma is equals to N1 by N2, and this is equals to R by R1. So T R by R1 is gamma eta by capital R. Next is energy consumption. Energy consumption. The movement of train between two stations can be approximated either by a trapezoidal or a quadrilateral speed time curve depending upon the service required, that is mainline or suburban service. I have already explained the trapezoidal and quadrilateral speed time curve. Now in order to stick to this speed time schedule, suitable amount of electric energy should be fed to the locomotive system. In case of electrical energy is to be supplied by a central power station or is to be tapped from a power grid. It is necessary to predetermine the amount of power required by the locomotive so that the power station equipments, substation feeders and distributors can be designed optimally. It is to be noted that while designing an optimally electric supply system for the railways, the reliability factor is of utmost importance. Now, as supply breakdown even for a short duration may result in a complete dislocation of traffic and may sometimes lead to serious accidents. And the degree of accuracy to which the electrical energy requirements can be estimated depends upon the exactness of the available knowledge relating to the conditions of operation such as schedule speed, distance between stops or frequency of service, the weightage of the locomotive, etc. And of course on the degree of the reliability requirements. So the electrical energy supplied to the train is spent in some ways. What are the ways? First, in accelerating the train on level track. Second, in accelerating the revolving parts. Third, in doing work against gravity, if the train is ascending a gradient. Next, in doing work against the resistance to motion and the last, in supplying losses to the motors and other electrical equipments. Now, for urban or suburban services with high schedule speed, the energy required for acceleration periods form a large percentage of the total energy required for the propulsion, whereas for mainline service on level track at high speed, the energy spent against the resistance, that is friction and windage, to motion may be considerably greater than that required during the part of the acceleration period, and the energy supplied during acceleration is stored in the form of KEA. Part of this energy is used during coasting and the remainder is dissipated partly as heat in the brake shoe and partly it is fed back to the supply system in case of regenerative braking is resorted to. Now, in the previous video, I have already discussed about tractive effort during acceleration, tractive effort on a gradient and tractive effort for resistance, and I have derived the expressions for tractive power for these three cases. Now, I discuss about power output from the driving axles. Power output from the driving axles. Now, the power output output from the driving axles at any instant of time is given by the product of tractive power and speed at that instant of time. Okay, tractive effort multiplied by speed gives the power output. Now, if tractive effort is expressed in Newton and speed in meter per second, then the power is expressed in term of watt. So, P, that is power output, is equals to tractive effort into speed or velocity. Now, Ft multiplied by V into 1000 by 3600, where V is in kilometer per hour. Okay, now if the tractive effort is expressed in kg, then P is equals to 0.278 into 9.81 Ft into V by 735.5 metric horsepower, which is equal to 3.7 into 10 to the power minus 3 Ft into V metric horsepower. Now, if eta 1 is the efficiency of transmission gear, then power output is equal to 0.278 Ft V by eta 1. Eta 1. What is eta 1? Eta 1 is the efficiency of transmission gear. Now, similarly, if eta 2 is the efficiency of traction motor, then power output is equal to 0.278 into V into Ft by eta 1 into eta 2. What is eta 2? This is efficiency of traction motor. Okay, now next, energy output from driving axles. Energy output energy output from driving axles. Now, the area under the power time curve gives the energy output during that time, or if the mean value of power over a period is known, then the product of mean power to the time under consideration gives the energy output during that time. And if power is expressed in watts and the time in seconds, the energy is in watt second or joule. Suppose we want to calculate the energy output when the speed time curve is approximated by a trapezoidal curve. The energy output during acceleration is given by half T1 into 0.278 Fa into Vm watt second. Now, energy output during free running time, this is during acceleration, and during free running time This is equals to 0.278 FA VMT2. FA dash VMT2. Now FA dash is the tractive effort during free running time. Tractive effort during free running time, which is different from the tractive effort during acceleration. Okay, now so FA dash is not equal to FA. Now sometimes it is more convenient for comparison set to express energy in terms of watt-second per ton kilometer of the train to include both the weight and distance travelled by the train, and this quantity is known as specific energy output and forms a basis of comparison between the dynamic performance of various trains having different passenger capacities and operating schedule. Specific energy output. The energy input to the motors is called energy consumption of the train, as it is the energy which is utilized for movement of the train, and specific energy consumption is defined as the energy consumed per ton meter. Consumed per ton meter. Assuming trapezoidal speed time curve, the specific energy output can be obtained as specific energy output during acceleration. Specific energy output during acceleration is half T1.278 into FA by VM to WD into 1000. Now this is equals to half Vm by, what is T1? Vm by alpha. We know that 0.278 into WT alpha into Vm by W into D into 1 by 3600. Now this is equals to 0.010726 Em square by capital D into We by W unit is watt hour per ton kilometer. Okay. Specific energy output against resistance. Similarly, if the tractive effort against resistance is R, the Newton per ton the specific energy spent against strain resistance is WR D dash by WD into 1000 by 3600, which is equal to 2778 R D dash by D. Now where D dash is the distance for which force due to resistance exists. Now similarly, the specific energy output during gradient next, specific energy output during gradient. Now tractive effort during gradient is (10 Wg into 9.81 Newton). Therefore, energy output is 98.1 Wg D dash into 1000 watt second. 98.1 Wg D dash into 1000 by 3600 watt hour. Now specific energy output is equal to 98.1 Wg D dash by WD 1000 by 3600, which is equal to 27.25 GD by D watt hour per ton kilometer. Therefore, specific energy output is equal to 0.010726 into Vm square by D into We by W plus minus 27.25 G D by D dash by D plus 0.2778 R D dash by D watt hour per ton kilometer.
That's all from today's class. If you have any problem, please contact with me. My contact details is given on the first slide. Thank you.